Welcome to M8307 numerical analysis class. In this lecture, we are going to learn Gaussian elimination with partial pivoting. First, we start with the definition. Using an equation to eliminate an unknown from the others is called a pivot, and a rule to choose pivot is called pivoting strategy. Okay, so a remark: obtaining an echelon form of an augmented matrix may necessitate row interchanges or pivoting. Okay, so this is also known as pivoting. We've just learned. An example: consider the following augmented matrix. So for this matrix, we cannot proceed without interchanging two rows, because there is no way we can eliminate the entry from here to here by multiplying 0 by any number. Okay, so this cannot happen, so we need to interchange these two rows. Okay, so once we do that and get the solutions, we easily find x1 equals 1 and x2 equals 1. So 1 will be 1, 1 plus 1 will be 2. Okay, so these are the solutions. Now also consider this example as well. So in this example, we change this position, this 0 position, with a small positive number. Okay, very small positive number, epsilon. So this will be negative epsilon, and this epsilon will be like 10 to the negative 10, for example. Okay, so positive but close to 0. So doing that shouldn't cause too much difference in the solution. So solution was 1 comma 1. So the new solution should be something very close to 1 for x1 and something very close to 1 for x2. Okay, but let's see if this is the really case or not. So an equivalent system with Gaussian elimination without pivoting can be found as this one here. So we put this system, this matrix into its echelon form. So to do that, we need to multiply the first row by 1 over epsilon, and then add the result to the second row. So once we do that, we will have 0 here and 1 plus 1 over epsilon here and 2 plus 1 over epsilon there. Okay, so now this matrix is in the echelon form, so we can proceed with the back substitution. Okay, when we do that, we see x2 is equal to 2 plus 1 over epsilon divided by 1 plus 1 over epsilon. So this is what we get for x2. And here, before moving on to the other unknown, let's discuss something here. So the epsilon, the number epsilon was very small. Okay, positive and very small. We said we give an example like 10 to the negative 10. So 1 over 10 to the negative 10, for example, will make it 10 to the 10. Okay, so this number will be basically 10 to the 10 plus 2. And here we will get 10 to the 10 plus 1. Okay, so if you're working with a machine with very high machine epsilon, okay, then this will cause a problem, because after some point, adding 1 to the number, if the number itself is large enough, adding 1 to the number will not change the number at all. So this number and that number will be basically the same. Okay, and this will be basically equal to 1. Okay, so once we obtain 1 from here, we get 1 from the other entry as well, for the other unknown as well. So x1 will be 1 minus 1 divided by epsilon. This will be 0 divided by epsilon. Epsilon is small but still a number, so 0 divided by a non-zero number will make it 0. So if we compare this solution with our original solution, which was 1 comma 1, we have quite a difference, significant difference in the first unknown. So this were supposed to be close to 1, but now it's basically 0. Okay, so it's too far from being correct. So let's also interchange rows and then proceed with the Gaussian elimination. Okay, so this was our augmented matrix, and we can interchange rows here, first row and second row, and then we can proceed to Gaussian elimination. And let's see what happens if we do that. Okay, so if we perform row swapping or interchanging these two rows, we will get this point, we will get to this point, and then we can multiply the first row by an epsilon and then add the result to the second row, just like we introduced here. Then we will obtain 0 in here. Okay, so which will make our matrix in its echelon form. Okay, so once we get there, we can use back substitution. Back substitution will give us x2 equals 1 plus 2 epsilon divided by 1 plus epsilon. So 1 plus 2 epsilon divided by 1 plus epsilon. So this is 1 plus very small number divided by 1 plus, again, a small number. So something close to 1 divided by some other number close to 1 will make the result close to 1. Okay, so this result will be close to 1. Okay, getting 1 for x2 and using back substitution for x1, we get x1 is approximately equal to 1, because x1 is 2 minus x2 and x2 is close to 1, so 2 minus something close to 1 will make the result close to 1. Okay, so now if we compare this with the original problem, solution of the original problem, it was 1 comma 1, so the small changes causes small change in the solution itself. Okay, what is the difference between this example and that example? Here we applied Gaussian elimination directly without any pivoting strategy, and we end up with an issue. And here we use some sort of pivoting strategy, and now we get better results. By better, I mean the result that we expect. Okay, so now a remark will follow. Gaussian elimination without pivoting is not a stable method. Since small perturbation, by small perturbation we mean we deviate the problem data by something small like epsilon. So it was 0, but in the perturbation we get negative epsilon instead. In the equation, since the small perturbation in the equation may lead to too much difference in the solutions. Okay, so for this reason we say Gaussian elimination is not a stable method. The pivoting strategy seems to be a reasonable candidate to resolve this instability, because as you can see from the example, we performed some pivoting strategy and it basically resolved our issue. Okay, so we get the solution being very close to the original problem. Okay, so we know there are lots of pivoting strategies. Okay, but the one we will cover in this course will be partial pivoting. Partial pivoting swaps rows only. Okay, and hence doesn't require any changes in the order of unknowns. Okay, so partial pivoting will only interchange only the rows. That means we are only changing the order of equations. Doing so will not change the order of unknowns. Okay, if instead we have performed some interchanges on the columns, then that would cause some differences in the in the solution itself. Okay, so since this is only row interchange, we don't have any issues with the order of unknowns, so they will remain the same. We swap the row having relatively small pivot element. Okay, so we compare the possible pivot elements. Okay, and then we basically swap the row having relatively small pivot elements with the one with the one below this rows. Okay, so next this will illustrate what we really do. We choose this row to we choose pivoting row to make sure the largest pivot element in its absolute value appear in the pivoting row. Okay, so we will see better in an example. And here we say it's possible we can have two numbers being the same in the pivot elements, and they both might be the largest pivot element. Okay, so if this is the case, we just choose the top one. Okay, so if this is the case, two or more numbers pivot elements are the same, then we choose the top one. Okay, let's see this process on an example. Consider the following linear system. So this is our linear system, and we put this linear system into its augmented matrix form. So once we do that, we will get to this point. Okay, here we see in the first column, indeed, we need to choose a row to eliminate. We need to choose a pivoting row and pivot element. So to that end, our possible candidates are 0.02 and 1. And we choose this one over here because this number is larger than this number in its absolute value. Okay, so this number is large, so we choose the largest possible in that column. Okay, largest meaning in absolute value. Okay, so we basically interchange the rows, row number 1 and number 2, to get this point. And then once we have the largest number appear as the pivot entry, then we can use this pivot entry to eliminate the other entries below it. Okay, so we can indeed multiply the first row by 0.02 and then subtract the result from second row to get 0 here. Okay, so once we do that, we need to modify all the second row, all the entries in the second row, so we will get here. Okay, now seems like we are done with the first column because all the entries but the leading entry of the first row is 0. So we are quite done with this part, and we can move on to the second row. In the second row, actually, I mean second row, and somewhat these rows and columns are connected to one another. So we are on the second row, but the pivot element will be chosen from this list. Okay, so all the possible pivot elements will be 0, 1, and this number. So 0 cannot be a pivot element because it's 0, and we cannot use 0 to eliminate other numbers. So two possible options will be 1 and negative 0.03. Okay, so if we take them in absolute value, we see the absolute value of 1 is greater than the absolute value of negative 0.03. So for this reason, we need to interchange these two rows. So row number 2 and row number 3 will be interchanged. When we do that, we will obtain this matrix. Okay, now we can proceed to cancel out this number to make it 0. So for this goal, we can multiply the second row by 0.03 and then add the result to the third row. So this will make this entry 0 and also modify the other entries as well. So the result will be this one. Okay, seems like we're in the very first two row and two columns we're done, and we can move on to the third row. Okay, here our our pivot elements, possible pivot elements are 50 and 0.04. It seems like 50 is larger than this number in its absolute value, so we need to interchange row 3 with row 4. So we will get here. And then we can use this row to eliminate the number from here. So this entry from here to make it 0. So to that end, we can multiply row 3 by this number. This is 0.0008. And then we subtract the, the resulting row, the resulting vector from the fourth row. So once we do that, we will obtain 0 here. Okay, and here we have 0. Okay, now if we check the matrix here, this is in the echelon form. Okay, so this is in the echelon form. So we can move on to the back substitution now. For back substitution, we have this number times x4 equals that number, so it's given here, and then 50 times x3 plus 100 x4 is 400, it's there, and following the same procedure, we can obtain two more equations. Now moving backward, here we have this number times x4 is that number, so dividing both sides but by the coefficient here, that will make 20 over 5, right? So this will be 4. x4 will be 4. So x4 is 4. And if you substitute 4 for x4, then this will be 400s, and this 400s will cancel out, and we will obtain x3 equals 0. And here again, x4 is 4, x3 0, 0 plus 4 will be 4. If we cancel 4s, we will have x2 equals 0 again. Okay, x2 and x3 being 0 makes x1 equals 1. Okay, so these are our solutions. To wrap up, we introduced partial pivoting strategy for Gaussian elimination because Gaussian elimination itself was not a stable method, because we worked with some we solved some problems with Gaussian eliminations and we saw there are issues with them. Okay, the small changes in the solution itself causes too much changes in the result of the Gaussian elimination. So that was quite a problem. So we introduced partial pivoting strategy, and we equipped the Gaussian elimination with this strategy to obtain better results. Okay, so that's all for today. Thanks for watching carefully. Bye.